Yeah. What happens when you go back to it? That's like I get when girls are not. No comment, but you don't want to. Seriously, too young. Too young. Too innocent. My ears can't take that. It's gonna, I'm making me straight from the path. Second one to load the track. Gave the taxes to go. So once it's in the books or serious. Interesting part. Yeah, so the books are like there were books. Can I get asked? What's the devil? This was Black Sabbath. Oh, MC. I was like, why is it so familiar? Yeah, that songs. Yes, I that song. You know what the devil man is? The devil man. Yeah. That was that's what I thought it was. He's taking so long. Very much crazy showing. I know something like seriously. Who's the lead guitar? It reminds me of like that shit. That doesn't matter. It's a lead guitar. He plays. I think he does play guitar. I mean, that's what I do. I saw him on my guitar. I remember him like I came up with like 4 5 years. It's sort of good. I remember one of my things. It's not it's just very bad. It's very yeah, like this. Same vibe. This one's good. But this one sounds like a Sunday. Wait. Once you guys to do it, there's two comments, but it's the original. I need to sign. First, you find they let these just how to get values that you can set aside. They just need like that. Because they the choice over one, they just look at what they do. I'm able to do the block and symbol mesh, not a symbol from polygon. Yeah. Well, it's snappy experience. Yeah, sorry. We do the block mesh differently. Wow, snappy hashtag. So yeah, that shows your object. Okay, I have to do some research on how to do what differently. Because if I get any of these, I'm actually going to talk about this. I'll write it down. Yeah, I feel like I'm like more down. I feel like all the conversations how do you use it for safety? And I just like, I need a mesh. So many things like, yeah, it sounds like you haven't even been everything from. I'm starting to find soon actually. You made to say that, but like, yeah, but like actually, like I think I'm actually gonna start this week. I think that's with all orientation happens in like.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Looks good. All right. So the plan for today is we are continuing with our lecture notes on the 1D equations, and so we stopped midway through the derivations last time, and so we're going to continue on with that. We'll see a lot more integrals, a lot more math today. So hope you guys are ready for it. In terms of announcements, the only thing that's out there right now are the midterm projects, and so make sure you guys are working on that. I think I've said it a few times, but the geometry, pretty much everyone's geometry is going to be more difficult than the tutorial. Not only is the geometry probably more complex than the tutorial, but also your image data is going to be a lot more difficult, and so the quality of the image data is generally lower. It's going to be harder to find your vessels, and the cross sections aren't going to be as clear. So you definitely want to make sure that you give yourself enough time to do the midterm project, because it's even just starting it can be a bit complicated, right? I think I've already talked to a few students this week about just finding out just where to even begin. And the tutorial said it was kind of easy to kind of find out where to begin, just because the aorta is just such a big beefy vessel. But if you don't have an aorta model, or if you have something else, even the aorta model is going to be a bit difficult to work with sometimes as well. So you want to make sure that you're starting early and get your questions in while you can. All right. So I guess now is kind of a good time to kind of talk about kind of the plan for the rest of the semester. So this week we're covering 1D modeling. We have a bit more theory next week in terms of what I call impedance, and then we have spring break. Okay, so spring break's after that, and remember that after the spring break, not the week after, I think not even for a couple weeks after that, we're gonna have like our exam in this class. So I call it the midterm exam. But it's kind of like a pseudo final exam, just because we didn't have a midterm exam midway through. So you definitely want to start kind of thinking about that in terms of studying for it, preparing for it, and everything like that. So I'll put out a study guide probably once we're closer to spring break, maybe right after spring break, just kind of help you out with that. But besides that, you know, the main things that are the main deliverables that you're going to turn in for this class are the midterm project, the midterm exam, and the final project. So those are going to be the three main things that are going to determine your grade in the class. And so, you know, you want to make sure you do well on all three of those. Okay. All right. Any questions I can answer before we get started for today? Yeah.
Is this and impedance going to be the last subjects we covered before the midterm?
We might do a little bit on 2D flow, so the oscillating flow stuff, depending on how quickly we can get through it. Because I want to stop, you know, the midterm exam. I think with midterm exam is planned for week 14. So I think we're going to stop the content for that week 13. So, you know, I want to leave kind of a weekly gap in terms of the content stop and the midterm exam. So it'll depend how far. But this stuff and the impedance for sure is going to be on the exam. Okay, all right, so let's go ahead and continue. All right, so where we left off last week. So actually, let me go ahead and scroll back to where we were last week. Okay. Okay, so what we were looking at last week was we were looking at the derivation of the 1D equations, right? And what we said was that the way that we're going to do this is we're going to take our Navier-Stokes equation, our conservation of mass and momentum in a flowing fluid, and we're going to integrate these equations across the cross-section of a vessel. Okay, so we already did the continuity equation, right? And so by integrating the continuity equation, we obtain this boxed equation right here. These are all from the notes last week, so you don't have to write these down again. Okay, and so that was our continuity equation, which says that the time rate of change of cross-sectional area in a vessel plus the rate of change of flow rate in the flow direction in z. When you add those things together, they equal 0. Okay, and we also discussed kind of the intuition behind that and why that is. Okay, so the continuity equation pretty straightforward. I think it has it's a partial differential equation, yes, which is scary, yes, but you know, in terms of physical interpretation, in terms of kind of understanding why the terms are there, I think it's definitely on the easier side. Okay. Where things get a bit more complicated is the momentum equation, right? So we were working primarily with this form right here, and we had already kind of simplified it. So we started with kind of the full Navier-Stokes equations and cylindrical coordinates. We applied some assumptions, mostly in terms of axisymmetric assumptions, which says that all the derivatives with respect to theta, the angle, go away. Okay, and so that leaves us with these 6 terms here. And what we were doing last Thursday was that we were integrating these 6 terms across the cross-sectional area and kind of simplifying their expressions to get our 1D equations, right? So we started that, and so we started with term 1 right here. So term 1 was the time derivative term, and so we took the integral of that, and we got partial q partial t. Okay, and then we did the second term. Which left us with this equation right here. Okay, so what we're going to start with today is we're going to go with the 3rd term, the 4th term, the 5th, and the 6th term, right? So it's going to be just kind of basically just all kind of derivations today. Okay, so let's go, just so my iPad doesn't blow up, let's go back to my other set of notes here. 1D. The name 1D equations is kind of a little bit of a misnomer. I remember when I first learned this and when I was in grad school, I thought, oh, 1D, this should be easy, right? But then, we spent, 2.5 full lectures of just doing derivations of integrals and derivatives. And so, yeah, definitely not as straightforward. So it is 1D, yes, but the fact that we have time there and we have multiple different variables that we're accounting for makes it challenging. Okay, so let's look at the 3rd integral. Okay. So that term was UR multiplied by partial UZ partial r. Okay. That's a term by itself, and so that's a term that you would have in kind of the classical Navier-Stokes, right? But in our treatment here for the 1D equations, we're going to take this, we're going to multiply it by 2 pi. We're going to integrate across the cross section, and so that means an integral from 0 to big R, or the radius of the vessel multiplied by r dr. Okay. So the terms in the black ink, that's the original Navier-Stokes terms, and then we're adding these terms, or we're applying these terms in the red. Okay. Okay. So this term by itself is pretty complicated for a couple of reasons. And so we have two, the main thing is that we have two different velocities here. We have the radial velocity UR, and we have the axial velocity UZ. Okay. Okay. Remember, radial velocity is the velocity that goes outwards towards the vessel wall. So that's typically the velocity that's used to expand and contract the vessel itself. And the axial velocity is the velocity that goes down the length of the tube. Okay, so that's the one that actually travels through your bloodstream. And the fact that we have both of those velocities kind of multiplied together here makes it challenging to work with. Okay, so we have to kind of work on this term a little bit to kind of simplify our life a bit. So let's work on the integrand. So let's take this integrand here, and let's see if we can put this in another form to make it a little bit easier to work with. Okay. All right. And by integrand, I mean everything there that's captured in the blue. So we have the UR, partial UZ, partial R, and the R as well. Okay. That R is not originally there. That R just came out just due to our integration, but it's going to play an important role in how we simplify this term. Okay. All right. So to simplify this, I'm going to pull something out of my ass for a second. So we're going to say that, all right, this term here, what if we obtain this term through a, remember what we call kind of a reverse chain? What that reverse chain rule looks like is not immediately clear, just because we have basically three terms here. But let me pull something out here. So what if we have this derivative here? So we have partial r of the quantity r times u sub r and u sub z. Okay. So we have three terms inside that derivative there that all depend on r. Okay. And so if we wanted to take this derivative or apply this derivative, we would have to basically use our chain rule. Okay. Okay. And so doing this, let's say that we have one term that is r times ur times partial uz partial r. Okay. Normally, this would produce three terms because we have three kind of terms here that are multiplied by each other. But I'm gonna collapse the second two, or the second and the third term into one. Okay, so this will be plus uz times partial r of r u sub r. Okay. So that term on the left becomes the two terms on the right through the application of the chain rule. Okay. All right. So the reason I did this is that if you look at this first term that comes out, right? That first term there, that looks familiar. Because that's exactly kind of what we have in this integrand here. It's just the r is kind of in front, except in the back. The commutative rule and everything, those are the same. Okay. So let's rearrange this term algebraically to solve for this term. Okay. So what that basically means is we're going to subtract that uz partial r ur term from both sides. Okay. And so what we get here is that r UR partial UZ partial R is equal to partial R of R UR UZ minus UZ partial R R UR. Okay. So all I did to go from the first line to the second line was I just subtracted this term in, let me highlight this term. So all I did to go from the first line to the second line was that I just subtracted that from both sides and then just kind of rearranged it a little. Okay. All right. This term right here, oops, this first term is good. Okay. Right. The reason it's good is because we have this entire expression taking the derivative, it's inside the derivative, right? Because eventually what we're going to do is we're going to take whatever we get in this expression here, okay, and we're going to plug it back into the integral. Okay. And if you notice, our integral up here is with respect to r, right? And so the dr from the integral is going to cancel out with the dr from the derivative, and that's going to make things easy for us to integrate. Okay, so that first term we don't have to do anything, and in fact that's kind of the main reason why we kind of did this whole thing, was so that we can get a term that's kind of a perfect differential. Okay, that second term we need to work on a little bit more. Okay, but luckily for us, this term here, we can actually simplify it a bit more using continuity. Okay. And not the 1D continuity, kind of our original kind of Navier-Stokes continuity. Okay. All right, because from the continuity equation, we have the following expressions. We have partial UZ, partial Z, plus 1 over R, partial R of RUR equal to 0. Okay. That's continuity equation in cylindrical coordinates, or Navier-Stokes. Okay. All right. And so if we take our continuity equation here, we multiply both sides by R and subtract partial UZ, partial Z from both sides. Okay. And so if we do that, we get partial R of R u sub R is equal to minus R partial UZ partial Z. Okay. All right, so what we can do now is we can take this expression here and plug it in back up here. Okay. And that's really clutch for us, because what that does is that for that second term, that eliminates UR from that expression. And we only have things in terms of UZ, which is going to be a lot easier for us to work with. Okay. Okay. All right, this integral, this term right here is probably the most complicated one, and that's kind of what I wanted to save it for today, because we did this at the end of class on Thursday, would have been more of a headache. But any questions on this so far? Everyone able to follow this? Okay. Okay. Okay, so let's go ahead and plug in for that. And so let me continue this down here. So this first term, like I mentioned, this one's good. So I'm just going to ignore that for now. So let's just work on this term right here. Okay. And so after plugging this in, So after plugging into that second term, what that term becomes is then R uz partial uz partial z. Okay, positive. And so that we have two negatives in there that cancel out. Okay. All right. So we can do what we can do from here is we can do another reverse chain rule. This one is mostly just for window dressing at this point. And so what we can do is we can transform this uz partial z into 1/2. So we have r times 1/2 partial z of uz squared. Okay. And if you remember from the end of class last time, we had a term that looked exactly like this. And so this is very, very intentional. Okay. All right. So let's plug all of these in. All right. So that includes the term that was good already and the term that we just found just now. Okay. All right. So that term, that integral, what we started out with was 2 pi integral from 0 to r of ur partial uz partial r times r dr. Okay. What we said, or what we just did just now, is that this integral here is going to split into two terms. So we have 2 pi integral from 0 to big R of partial r. This is our first term here that was good before. This is r ur uz, okay, times dr plus 2 pi integral from 0 to r of what we just found up there. So r times 1/2 partial z of uz squared dr. Okay. All right, so let's simplify this. And so for this first integral right here, the partial r on the bottom and the dr are going to cancel out essentially. Okay. A little voodoo math, but you know it works. Okay. There's a longer, kind of more mathematically correct way to explain why that is, but you know I find this just to be kind of the most easiest. Okay. And so what that allows us to do is that allows us to kind of directly integrate the integrand. Okay. So this is now a perfect differential. So it cancels with the integral. Right, so this gives us 2 pi. Whatever quantity was inside there, so r times ur times uz. Okay. So that differential cancels out with the integral. But we need to evaluate this at the integration bounds. And so the integration bounds here are big R and 0. Okay. And so what that means is that we plug in our integration bounds here, we have 2 pi times that entire expression there evaluated at big R. So we have big R, ur at r is equal to big R, and uz at r is equal to big R. Okay. Minus the entire expression evaluated at little r is equal to 0. So we have 0 times ur at r is equal to 0 and uz at little r is equal to 0. Okay. All right, so let's look at this term. So before we get to the second integral, let's evaluate this and let's just finish it out. Okay. The second part of this, after the minus sign, we have 0 times UR at R is equal to 0 times UZ at R is equal to 0. Okay. We know that this term is equal to 0 because 0 times anything is 0, right? So we know that term goes away. Okay. This first term, believe it or not, also 0. Okay. Why is that? Because we're evaluating U sub Z. Okay. Remember, U sub Z is the axial velocity of blood going down the length of the vessel, evaluated at the wall. Okay. That's R is equal to big R. And so because of the no slip boundary condition, we know that this must be equal to 0. Okay. This is no slip. And so that means this entire integral here is equal to 0. All right. So there's a lot of work to show that something is equal to 0, but that's kind of the beauty of math sometimes, that you do all this work and then you realize you could have just done nothing and then it would have been the same, right? All right, any questions on that? Everyone kind of understand kind of why that term there cancels out, why that's 0? Good. Okay, so let's work on the second integral here. Okay, so for the second integral, we have a 2 pi on the outside and a 1/2 on the inside. So first thing we'll do is we'll cancel out that 2 with that. Okay. Next thing we'll do is well, let me just kind of write it down after that. So after that, we have pi times integral from 0 to big R of partial z of uz squared r dr. Okay. And that's as far as we can go, right? Because we don't have an expression for uz right now. So unfortunately, we're just going to have to leave this as it is. But, if you look back at the end of our notes last time, we had a term that was literally exactly the same as this. Okay. So even though it seems like, we did all this work and we kind of hit a dead end, at least we hit the same dead end, right? So we can basically combine this together with the work that we did last time to get kind of one big term. Okay? And so we'll deal with both of those together. We're not leaving it just like this. We are going to deal with it. It's just we're not really ready for it at this point. Okay? All right. So that's half of the Navier-Stokes equation out of the way. But we did get the most gnarly term. Okay. So now we just have the pressure term and the 2 viscous terms of Navier-Stokes left. Okay. All right, so let's take a step back and kind of see where we're at. So I'm going to go back to our lecture notes from last week. Okay. All right. So this is where we started, right? This is our momentum Navier-Stokes equations. And so we've done the first term. Okay. So that first term is basically just partial Q partial T. That's what you see at the bottom of the screen. We did the second term as well, kind of. Okay. And so when we integrate the second term, this uz partial z, we ended up with this equation right here, this pi integral partial z uz squared. Okay. So this one's on hold. Okay. And then what we just did for the first half hour of today's class was we did the third term here, which again, we kind of did it. And so we simplified it as much as we could, but for now it's on hold. Okay. But at the very least, we were able to manipulate the third term to be the same as the second term here. So at least now they have a buddy. Okay. They're waiting on hold together. Okay, so now let's deal with the last four terms. So, or the last three terms. So we have the pressure term and we have the two viscous terms, the terms that have viscosity. Okay. Okay. So now let's deal with number 4, pressure term. Okay. So the pressure term in Navier-Stokes is a minus 1 over rho partial P partial Z. Okay. And then once again, what we're doing is we're integrating this. And so we're integrating from 0 to big R, multiplied by 2 pi, and R dr. Okay. All right, this term is very simple. Okay. No more reverse chain rule, none of that shenanigans. Okay. Because what we can assume here is that we're going to assume that the pressure and the density we're going to assume the pressure and the density are uniform across the vessel cross section. Okay. In other words, they do not depend on R. Okay. And so what that essentially means that we can pull those out of the integral. And so we have a minus 2 pi times, let me do it like this actually. Let me do a minus 1 over rho partial P partial Z multiplied by 2 pi integral from 0 to big R of R dr. Okay. Okay. So this is great, right? In fact, we skip all integration at all, because what this quantity is, right? If you carry out the integration here, we get an R squared over 2. Okay, we evaluate that from 0 to R, and we get an R squared over 2 times 2 pi. And then you multiply that, you get pi big R squared, which is nothing more than just the radius of a circle. Okay, not the radius, the area of a circle. Okay. And so this term right here, this integral, just simply becomes minus area divided by density multiplied by the pressure. Okay, so we have minus A over rho times partial P partial Z. And this one is good. Okay. All right, so the pressure term only took us 2 minutes as opposed to 30 minutes. So a lot easier to handle. All right, any questions on the pressure term? Okay. All right, so now we have the two viscous terms, right? The two terms with viscosity. All right, so this is term 5. This is viscous term 1. Okay. All right, so viscous term 1, we have a rho or nu divided by R times partial R of R partial UZ partial R. Okay. And just like before, we're going to integrate this. We have a 2 pi integral from 0 to big R of R dr. Okay, so we have another pretty straightforward one here, because we're going to have a lot of terms that cancel out, and we can factor it out. Okay, so first thing we notice is that we have an R in the denominator here and R in the numerator here. So those ones are going to cancel out. Okay, so that's pretty convenient. The other thing that we'll do is that we know the viscosity. The viscosity is just a property of the fluid itself, and so it's something that doesn't change with R as well. So we can pull it out. Okay. And so if we do that, we get 2 pi times nu integral from 0 to big R of partial R partial uz partial R dr. Okay. All right, so now it's more time for more voodoo math. And so we have the partial R and the dr and cancel out. And so what we have once again in the middle here is a perfect differential. Okay. And so that perfect differential is gonna cancel out with the integral. Okay. And so this is going to be 2 pi times nu times quantity R partial uz partial R evaluated from R is equal to 0 to R is equal to big R. Okay. Okay. So we know the 0 side of this is going to be 0, right? So if we plug in 2 pi nu big R partial uz partial R evaluated R is equal to big R minus 0 times partial uz partial R evaluate R is equal to 0. Okay. We know the second half of this is going to be 0 because we have 0 times something, right? But that one's going to be 0. Okay. The first part of this, we actually can't cancel the 0. So we know that uz itself at R is equal to R is equal to 0, right? That's our no slip condition. But what we have here is not uz, but we have the derivative of uz with respect to R. Okay. So this term we can't really do anything with it. So we just kind of leave it as it is. And so this entire expression here then becomes 2 pi times nu times big R partial uz partial R evaluated at R is equal to big R. Okay. And this is another one where this is as far as we can take it. Okay. So we'll leave this as it is for now. All right. So we are able to fit this entire step into one. Any questions on how we did this this integration here? All right. So that's viscous term number 1. Last but not least, let's do viscous term number 2, the last term in Navier-Stokes. Okay. So viscous term 2, what we have here is nu times partial squared uz partial z squared. Okay. And just like all the other terms, we're going to apply our integration to it. So we're going to multiply by 2 pi, integral from 0 to big R times R dr. Okay. All right, so we're gonna do the same trick that we did earlier, was we can see here that we have a derivative with respect to z. So let's pull that out. Okay. And let's pull out the 2 pi nu as well. So we have 2 pi nu partial squared partial z squared. Okay. So all I'm doing here is just pulling out the z derivative. Okay. And then we get integral from 0 to big R of uz r dr. Okay. We know what this is, and so this is nothing more. Actually, if we put the 2 pi here as well, so we put the 2 pi there, that quantity is the flow rate in the vessel. Okay, which is Q, right? And so if we plug in Q for that integral there, and we apply our Z derivative, this term here is nu partial squared Q partial Z squared. Okay. All right. So all the integration's done. We're no more integration for today. Okay. At least not for Navier Stokes. All right. So now we have integrated all the terms in our momentum equation. Okay. So it only took us, 40 minutes a day and then maybe 20 minutes last time. So it only took us an hour to do so, but we did it. Okay. But we're not done yet, okay? Because we have a lot of terms here that are still not really usable. At least yet. Because ideally, when we set out, when we started this whole process, right, and the whole motivation of doing these 1D equations was to kind of eliminate a lot of the unknowns in the equations, right? So we want to kind of simplify Navier Stokes. That was our goal. So we would like ideally like to have equations that only involve Q and A. So the flow rate and the cross-sectional area. Because if you think back to our continuity equation after we applied our integral, those were our two main variables, right? Of course, there'll be things like derivatives, and there'll be things like the material properties of the fluid in there as well. But those are okay. Those are fine. What we have right now are kind of a lot of other things. Okay? Right. So primarily we have two, we'll call them unwanted guests. Well, one of them is unwanted. The other one is like kind of unwanted. We just want him to change his clothes or something. Right? So our two unwanted guests are the velocity uz, right? So if you look back at a lot of the terms that we ended up with from our integration, that was one of the main ones. Okay? So this one's unwanted. So we need to do something about him. Okay? The other one is the pressure, actually. So the pressure by itself is fine. And in fact, getting equations for pressure is something that's actually really valuable from these equations as well. We just don't want to solve for it primarily, right? So we need something else to kind of put this into a different form. Okay. All right. So the next parts of the lecture, probably what's going to take us to the end, is how we're going to deal with these two specific terms. Okay. And then probably what we'll do Thursday is I have a code that kind of solves these equations for you, and then we'll kind of go through that code together. But I think today we'll just focus on finishing up the derivation. Okay. All right. Any questions on this so far? Okay. So let's start with UZ. Okay. And so UZ UZ here is a function of R. Right. We've worked with this previously, right? So this is not our first time seeing UZ in this class. And so if you think back to our review of fluid mechanics, when we solved our Navier-Stokes equations in cylindrical coordinates in our blood vessel, this UZ here represented the velocity distribution or the velocity field within a blood vessel. Okay. And so if you have a particular blood vessel here, right? You have blood that's flowing through the blood vessel. UZ there tells us, how the velocity of the blood varies as a function of the radius, right? Right. So if you recall from, our fluid mechanics review a long time ago, right? What we saw was that this velocity profile was parabolic in shape. And so it had a peak in the center of the vessel, and then it went down to zeros at the edges. Okay. All right. So the fact that our equations here, our integrated equations still have UZ, what that tells us is that we need to essentially we need to make an assumption about what the velocity profile looks like. Because we're kind of up the creek without that, right? Because if you look back at a lot of our derivation, right, we had terms that look like this, right? So we're taking the derivative with respect to R, right? We can't do anything until we plug in for UZ. Okay. We have this other term, the term that we spent the first 30 minutes of class working with, right? So we have partial Z of UZ squared, right? We can't do anything until we plug in for UZ right there, right? And so the only way to move forward is to make an assumption on what the shape of the velocity looks like. We don't have to give an expression of what it is exactly. We just need to know kind of what its rough functional form looks like, and then we can apply our derivatives and integrate and kind of finish. Okay. All right. So there's a lot of options here. So there's a lot of different options for the profile shape. The simplest one that we can do, and the one that we're going to opt for, is the parabolic velocity profile. Okay. Which, if you recall, our parabolic profile was our solution to the rigid steady Navier-Stokes. Okay. So of course, we're trying to lift those assumptions, and so we're looking at a situation that's not steady, that has deformable walls, but we're stuck here until we make an assumption, right? Eventually we're gonna discuss what the velocity profile will look like when we have a deformable wall and when we have unsteady flow. Okay, so that's gonna be our 2D stuff that we're gonna cover after spring break. But for now, just so that we can move forward, let's assume our parabolic profile. Okay. And so if you recall, our solution for that, this was kind of way back in week 3 of the semester, or week 2 or something like that, was UZ of R is equal to 1/4 mu times dp dz times little r squared minus big R squared. And in particular, if we take this UZ and we integrate it across the profile, we get the flow rate. We get the flow rate of the vessel, a flow rate of blood in a rigid wall vessel with steady flow is equal to minus pi r to the fourth divided by 8 mu dp dc. Okay. So this is the flow rate. So that's the flow rate of blood in a steady rigid wall vessel. Okay. Okay. So let's use these two expressions here. Okay. Because it would be great if we got our velocity in terms of Q. Okay. So let's try to plug this in. Oops. Okay. So we're going to plug into the top expression so that we get UZ of R as a function of Q. Okay. And the main way that we're going to do that is we're going to plug in for part of dp dz. Okay. Okay. So for the interest of time, we only have 25 minutes left. I'm just going to go ahead and do that. Okay. But if you can imagine here, you can solve the second expression for dp dz and then plug that into the top expression there. Okay. And then we can plug in for the area as well, because area, remember, is pi r squared. Okay. And so if we do that, we get the following expression. Okay. We get UZ as a function of R is equal to 2Q divided by cross-sectional area times big R squared times R squared minus little r squared. Okay. All right, so now what we can do is we can take this. Now that we have an expression for UZ that has both our flow rate and our area, we can plug this back into our momentum equation and kind of finish out our derivation. Okay. Okay. So basically everywhere we see UZ, we're going to plug this guy in for that. Okay. All right, so there are two main places where this happened. On the one side, we have in the convection terms. So we had two terms that were exactly the same, and then we had one of the viscous terms that had this as well. Okay. All right. So let's start with the more difficult terms. So this is going to be terms 2 and 3 together. Okay. So if you recall, what we had here was 2 pi partial z of integral from 0 to big R of UZ squared dr. RDR, excuse me. So those are the integrals where, we took it as far as we could, and then we kind of stopped, and because we said we couldn't proceed anymore. Okay. So let's take what we have for UZ and plug it into here. Okay. Now, unfortunately, this does mean that we have to square it, which is a little bit annoying, but we can do that. We've done literally every other piece of math in the book today, so squaring something is not that big a deal. It is a big deal, but at least it's not calculus. At least it's just algebra from there. Okay. All right, so 2 pi partial z of 0 to big R. We plug in for that, we square it, we get 2q divided by a r squared, quantity squared, multiplied by big R squared minus little r squared squared r dr. Okay. Okay. And let's go ahead and FOIL this guy out. Okay. The 2q over ar squared, that term, it doesn't depend on r, so we can pull it out of the integral, but it does depend on z. So we need to leave it inside there. Okay. All right, so let's go ahead and FOIL that out. So we have 2 pi times partial z of 2q over a r squared integral from 0 to big R. We FOIL this out, we get r to the 4th minus 2r squared little r squared plus little r to the 4th times r dr. Okay. All right. So I'm just going to work on the integration portion of this. Okay. So, you know, this other part here, we'll bring it back later. Okay. So in case you're kind of just, you know, following my work line to line, if you're curious about where that part goes right there. Okay. All right, so inside this, we have integral from 0 to big R. I'm going to multiply this little r through everything. So we have little r times r to the 4th minus 2 big R squared little r cubed plus little r to the 5th dr. Okay. All right, so let's go ahead and apply our integration here. So we have little r squared r to the 4th divided by 2 minus big R squared little r to the 4th divided by 2 plus little r to the 6th divided by 6, evaluated between 0 and r. Okay. So the 0 side of this is going to be 0, right? Because we have all little r's there. So we only have to worry about the big R parts. Okay. So the big R parts, we have big R to the 6 divided by 2 minus big R to the 6 divided by 2 plus R to the 6 divided by 6. Okay. We have an R to the 6 over 2 minus an R to the 6 over 2. And so those two terms are going to cancel out. Okay. All right, and so now let's go ahead and bring everything back. So we have a 2 pi times partial r of, I'm going to go ahead and square this first term here. So if you square that first term, we get, let's see, we get 4 pi or 4q squared over a r to the 4th, okay, multiplied by to the 6 over 6. We're going to have a lot of terms cancel out here. So we have an r to the 4th on the bottom. That's going to cancel out with an r to the 6th up top. And so up top here, we're just going to have a big R squared. Okay. Let's bring in this 2 pi. Okay. So the 2 pi is just a constant. So you can kind of bring it in and out of the derivative there. Okay. Sorry, this is a c derivative. Okay. So it's partial z. Okay, so then we have partial z of 8q squared times pi r squared divided by a times 6, or 6a. A6 looks weird. Now I want steak. Okay, Oh, sorry, this is a squared on the bottom. Yeah, okay. Yeah, we need an a there. Okay. All right, so we have pi r squared. Pi r squared is just a. Okay. So the a up top is going to cancel out with the a on the bottom. And then we have 8 over 6. They have a common factor of 2, so 8 over 6 is going to be 4 over 3. And so all we're left with from here is partial z of 4q squared over 3a. All right, a lot of work there, a lot of FOIL, a lot of integration, a lot of simplification, but we're here. Okay. Relatively innocent looking term, but this term actually is kind of a headache to evaluate because it's non-linear. All right, any questions on how we got to that point right there? I know it's intense. It's probably the most intense math day that we'll do this semester, but you know, we're just about there, I promise. All right. So that's terms 2 and 3, so that's good. But we have one more term in our momentum equation that had UR into it, or UZ, excuse me, which is term 5, a viscous term. Okay. And so term 5 here was 2 pi times the viscosity nu times R, partial UZ, partial R, evaluated at R is equal to big R. Okay. All right, this one's a lot simpler because we don't have to, you know, we don't have to FOIL anything or integrate anything. We just plug in and take the derivative. Okay. So let's plug our assumed profile here. Okay. And then we're going to take our derivative with respect to R. If I could spell. All right, so we do that. What we get is, I'm going to bring the 2 on the inside too, just to make it a little bit easier. So you have a pi times nu times quantity. We evaluate everything, all the little r's at big R. So we have big R times minus 2q divided by a r squared times 2 times r. Okay. Oh, 2 pi. Brought the 2. Okay. Okay. So a lot of these terms here are going to cancel out. So we have an r squared on the bottom. That's going to cancel out with our 2 r's up top. Okay. So that r is going to cancel. That r squared is going to cancel there. Okay. Up top, we have 2 times 2 times 2, which is 8. And so this term right here, once we kind of, once all the dust settles, is a minus 8 pi nu times q over a. All right. We're now ready to write down the 1D equation. So about 1.5 hours of lecture time of just pure math, torture, integrals, derivatives, polynomials, all that stuff. We're finally ready. Okay? So finally. Okay. we can finally present the 1D equations without any velocity terms, okay? Okay, so let's write it down. So let's start with continuity. For a continuity equation, our mass equation is partial A partial T plus partial Q partial Z is equal to 0, okay? That's what we did last time. So this is our continuity or mass equation. So this is mass conservation. Okay. And then the expression that we've been working, for the past hour and a half on, the momentum equation is the following. Okay. So momentum conservation, we have partial Q, partial T plus partial Z times 4 over 3 Q squared over A, okay, plus A over rho partial P partial Z is equal to minus 8 pi nu Q over A plus nu partial squared Q partial Z squared. Okay. So that right there is our momentum conservation equation. Okay. All right. Any questions on any of this? How's that there? Yeah.
For the first viscous term, is there like a reason like why it's like, not really a reason, but like, can we also use Q over A and simplify it to average velocity? Or is there a reason why we use Q over A?
Yeah, no, that's a really good point. So Q over A typically is the average velocity. But the reason we have it as Q over A is because we want our two equations. So these are our two equations here, and we want to solve them in terms of Q and A. Because we plug in velocity in there, that kind of introduces another variable that we're not really ready to solve for. So, but you're absolutely right. So in traditional Navier-Stokes, Q over A would exactly be the velocity. Yeah, and that's essentially the origin of that term. You have 8 times pi times nu, which is like kind of like the circumference of the of a tube. Not really, but it's around there. Multiplied by the viscosity times the velocity. So that's essentially where that term originates from. Yeah, that's really good observation.
This equation is used to find the velocity, right?
You could. And so you kind of have to do it in kind of a backwards way. So you first solve these equations for Q, and then you go back to our assumption of a parabolic velocity profile, and then you can use that to solve for U.
If we were like given, like let's say like we had like some sort of problem that was like given the average velocity, could that be replaced with a constant Q over A?
Yeah, so that would be an assumption of like we call it like a plug profile, so kind of a constant velocity profile. You can definitely do that. Yeah, the complication is that exact profile doesn't happen a lot in the cardiovascular system. So that's why we assume the parabolic profile. Yeah. All right, so these are our equations. We did all that work, but unfortunately, these equations are still partial differential equations, and even more bad news is that we have some nonlinear terms here. So we have this term and actually this term as well. Okay. So these terms actually by themselves are almost impossible to solve by hand. So we did all that work to derive them, and they're still not solvable by hand. So that's kind of a little bit frustrating, a little bit defeating, right? So, the whole point of going through this whole exercise of integrating Navier-Stokes was to make it easier to solve. And we went through all this work, and it is easier. And that's one thing you just kind of have to, just kind of trust me, bro. It is easier to solve. It's just that, when you can't solve it by hand, it's a little bit hard to see. Okay. But because of this nonlinearity, we do have to solve this by code. Right, and the way we say that is that this is solved numerically. Okay. It's just that writing a code to solve this equation is a lot easier than writing a full CFD code. So when I took this class or kind of the equivalent of this class in grad school, we basically kind of stopped right here. And then the homework assignment was to write a code in MATLAB to solve this equation. So we're not going to do that. Don't worry. I'm not going to make you write a code to solve this. I already have a code to solve it. It was actually my homework assignment back then. And so what we'll do next time is we'll kind of analyze that code and kind of see the results from there. Okay. And trust me, it is a lot easier. And in fact, this 1D equations can do a lot of things that some CFD codes can't. Because a lot of times when you use a CFD code, and you guys will see this when we do our final project, doing deformable walls or walls that kind of are flexible is really, really difficult. So the fact that these equations here have those deformable walls kind of baked directly into the equation is actually really, really clutch. It's actually really, really nice. That's really hard to do in 3D. Okay. But I think for today, I think we'll stop here. I think that's kind of enough math for one day. And so when we come back on Thursday, we'll go ahead and finish this up. I'll show you the code, how to run the code, and we'll talk about the pressure term. So the pressure term is kind of one last thing, one last piece of the puzzle done. Okay. All right. So thank you guys for coming today. Thanks for humoring me. I could talk about math and do these derivations all day, but I know it's not the most popular thing, but I appreciate you guys coming and listening to me talk about it. Hope you guys have a good rest of your day, and I will see you all on Thursday.
This is non-linear. It's not accurate.
These are non-linear because these are your two variables right here. And whenever you have like a division or multiplication of two variables, that makes it honest. If you look at most differential equations, it's a limit. I think people don't notice it first when you have your limit that have higher orders. But if you look at the variable itself, in most differential equations, there's no exponent on that point. Those are all linear equations. Where you have q over a or even like q squared, that makes the equation wrong.
Yeah.
And actually non-linear makes it exponentially more difficult. It's not impossible.
I get there, like, I'm just trying to I still, so I get opposite the squares, immediately, it's not a better.
Yeah.
Relationship, but this one, even though they're both to the first power, so you know what I mean, like, how I would, it's just because they're both variables.
Exactly.
Variables.
Exactly. So if you kind of think of q and a, think of like imagine they were both. Well, you have q times a to the minus 1.
Oh, you're right, yeah, okay, that's technically, okay. Is the negative one part,
Yeah.
Okay.
Anytime you have an exponent that's not 1, that's not linear. So even if this was just 8 pi mu over a, that would be not. That would be a to the minus 1.
And then the rest are constants,
Yeah.
8, 5.
Yeah. Exactly. This one's linear. This one's linear because dPdz is this.
But yeah.
Yeah.
P, it would be your term that's the linear part, right?
Exactly.
You're looking at the index for the exponent of that.
Exactly. And this term is linear too. We set a huge.
Well, we take, that's kind of question about like, you were kind of how you would put it, I guess. So is that something you would have to like, I don't know, use a code like discretization like and then like put it into like a matrix and then like put that
Exactly. Yeah. So you'll see next time. The method we actually use for this is
Yeah.
So basically, we make a grid.
Make sure you
We make a grid.
that's the whole like.
And then we basically take the finite difference of each. Because finite difference actually can go not here.
Well, things like.
Whenever you have a modern one, you find it.
Yeah.
Because we've done a couple, at least for CFU, we've done a couple non-linear. Financial working problems, but the only like kind of like issue I see when I look at this is like having that Q over A.
Yeah.
Because typically you want to like separate the variables,
Right.
but that Q over A kind of makes sense.
It does.
So you have like one side for A and one side for Q, and then you would make your matrix.
Pretty much, yeah. You solve it in a couple of ways. You can have two matrices that you kind of solve. the same.
Oh,
It's weird. I'll have to look at the coding 100% to make sure. But yeah, we'll go over it.
So it's not like a traditional like AX equals B.
No, it is. Eventually it gets to that point. And eventually I think you put it all into one, so you kind of form the Q side and the E side separately.
Oh, okay.
We'll see. I'll need to look at the coding and just.
Okay.
And I don't know how much I want to get into it, because it's gonna be a lot of.
Yeah, it's a.
But yeah, I'll try to basically give a good overview.
For sure.